I'm going to see you during the presentation, so you cannot hide anymore. I'll catch you there. So for chemical equilibrium, okay, this a little anatomy of this naming thing, that how this, what is this equilibria and what is this equilibrium is coming from. So equilibrium is this term is coming from equal, from the equal this thing, and sometimes it's in shortened form it's called equilibria as well. So this from the name we understand that there is something going to be equal at some time, and then in chemical reaction most of the thing that we do is in a broad form, that it is reactant and product. So what could go, can be equal between these two? Concentration, amount, the volume, what is the equal between them? That is the thing that we are going to see actually. What does this equilibrium tell us, or what does it actually mean? Why we are calling it chemical equilibria? And then this term is chemical is coming from, is associated with this equilibria or equilibrium. So what does it actually tell us? So for us, the learning outcome or objective from this is, what is the features of chemical equilibrium? That means, what do we expect from this chemical equilibrium or chemical equilibria? Sometimes I have a bad habit of calling it equilibria, but both the same thing. How do they attain the chemical equilibrium? What are the things that we can expect from the chemical equilibrium? What are the information we get? And how does it occur? Where does it occur? So all these features and these questions, we will look to find the answers from here. All right. Okay. So this and also, if we want to find the answer quantitatively, all of you, I'm sure that already know that what is qualitative and quantitative, right? Qualitative means you cannot measure, but you understand good, bad, worse, left, right, up, down. You understand, that is qualitative. But we cannot make people understand or make people think that this is good as much as I think. Probably it is different from them. This is because of we cannot measure it. But for quantitative means I know exactly how tall it is, 100 meter, how long it is, how big it is. I know exactly the figure. So if I say that this is 1 kilo, somebody else cannot say that, oh no, I don't think it's 1 kilo, it's maybe 2 kilo. No, because I have the kilo, 1 kilo, this is the unit. I can measure it with some kind of unit, so that is qualitative. Okay, that is the previous topic. I already talked about it, just now talking to refresh your memory. So from this equilibrium constant, when there, there's another term, right? Equilibrium constant is coming here. Because of this equilibrium, there will be some constant. We will see it later. And from this equilibrium constant, we qualitatively can understand, can find out how much of the product or reactant is there. Of course, we understand that the reaction happens. The reaction go from left to right, from product to reactant side or reactant to product side. But how much of the reactant and product is there in the system? The system here is the whole thing. The reaction is occurring. Not only the reactant and product, not only that, but in the vessel, in that reaction chamber, the reaction is occurring. The temperature, the pressure, the size, everything all together is the system. Okay, this is the system. So the equilibrium is happening in a system. It is not a thing that you just throw it somewhere and it is happening. It is Maybe it will happen, but we are not considering that. We have to see it, to quantify it. We have to do it in the lab, and then we have to find out. So that is why we're calling it equilibrium system. And afterwards, when we understand what is the equilibrium constant, chemical equilibrium occurs, what is the factors that it affects the chemical equilibrium, all those things, when we are done with this, when we understand with this, then we will see the Le-Chatelier's principle and what does it tell us. Okay, there is a Le-Chatelier's that a French scientist, chemist, not chemist, that time actually, the physicist, chemist, all of them. So a scientist, he gave us told us that when a chemical equilibrium happens, how do we predict it? Where does it go? Which side will it go? Will more product will form or less product will form? Or what? How do we predict it? The direction of the reaction. So this is the last our learning objective. Okay. So to understand the chemical equilibria, the first one, we see the production of ammonia. Those who could came to the lab, for our first or second tutorial that we had in our face-to-face, I was discussing about this ammonia. Those who came, you can remember. But this is ammonia, and this ammonia is, there are a lot of usage for this ammonia, a lot of usage. And this is mostly fertilizer, all right? 70% of it is fertilizer, and there are metal extraction, then explosives, other things, other metal works we need, but mostly we produce is the fertilizer, the ammonia. From this ammonia, the urea production, the urea, and that is why nowadays we have surplus in food production. Agricultural production, we have surplus because of this fertilizer. And after 1950, we do not have any famine. There is no, natural cause that we didn't have enough food production this year, so people were hungry. No, not. There are famine, some part of them, but this is political and man-made thing. Okay, so because of this, is so powerful thing. This is a very useful our modern. This is one of the best thing that chemistry give us for our living and well-being in the modern life. But this is so simple, right? Nitrogen and hydrogen you mix together, and then you get the ammonia. And as the reaction, del H tells us this is an exothermic reaction. That means it will produce heat. The reaction will produce heat. So, and from the reaction, we also see that 1 part or 1 mole of nitrogen, if we mix with 3 mole of hydrogen, it will produce 2 moles of ammonia, right? From the reaction, and this is true. This is the reaction actually. This is the chemical reaction that the ammonia is produced this way. But this is not quite the same. It is not like you make one, you put in the vessel or the system 1 mole of nitrogen and 3 mole of hydrogen, and then after some time you go out and have a cup of tea, and then come back, and then you get 2 moles of ammonia. It is not that simple. There are some other things that we have to take in consideration. What is the other thing? These both arrow is the other thing, right? This is the other thing. This arrow tells us that this reaction can go to produce ammonia, as well it can go and break down to nitrogen and hydrogen at the same time. This arrow, double arrow, means it can go on the both sides. So this is the problem, that I will not get 2 moles of ammonia anytime if I leave it. I have to do some engineering on it to get more of the ammonia. And that's why chemical engineering born, to maximize, the product. We know that what chemistry does, how chemistry works, but we do not get what exactly we're expecting from this chemistry or chemical process, because there are some other engineering related to this, and that is why the chemical engineering is important. Anyway, so this is, we will not get the 2 moles of ammonia because there is a reversible reaction, and that is why it will break down, and then it's called the system, if the system is in the closed system. Hold on, yeah, I need to something here. Okay. So this is the thing. So the reversible reaction in a closed system will achieve, and since this is a reversible reaction, right? It's a reversible reaction. That means it goes forward to produce ammonia, and it goes backward to produce, or reverse. It goes reverse. I don't call it backward, but it's better to call it reverse, to produce and break down to nitrogen and hydrogen. And this is going on at the same time. At the same time means like this is from nitrogen and hydrogen, it is going to produce ammonia. At the same time, ammonia is breaking down to nitrogen and hydrogen, right? So now you understand that since ammonia is producing at the same time ammonia is breaking down, there should be some time where it will be at the equal moment. That means how much ammonia is being produced, at the same time that much ammonia is also breaking down. So sorry. So this one, this nitrogen, and it is happening in the closed system. That means if we take a closed vessel, this is a bad design, bad drawing. How do I make a closed system? Let's say this is a bottle, and this bottle, I close it. Here, this is a cap. So this reaction is happening in this bottle, and this is tightened. The cap is not loose. There is no leak. It's happening here. So ammonia is being produced, and then the ammonia, the same amount. At the beginning, of course, there is no ammonia. So in the next slide, we'll see it. So when the amount of ammonia is being produced and the same amount, like how much I say that, okay, 1 gram of ammonia is being produced. This G is not gram, yeah, it is gas. This is gas. This is gas, it's not gram. 1 gram of ammonia is being produced there. And at the same time, 1 gram of ammonia is being dissociated to nitrogen and hydrogen. So you see that same forward and backward reaction rate is same. 1 gram is producing, 1 breaking. So exact same, the reaction rate, forward and backward, reverse reaction rate is the same. And when the reaction rate is same, at some time they will reach to an equilibrium. Okay, they will reach to an equilibrium. At this equilibrium, it will seem that the reaction stopped. Reaction is not happening anymore. Okay, it's done already. But underneath that screen, that what we can see, the reaction is continuing, actually going on. Forward and reverse reaction is continuing to grow, produce the ammonia and nitrogen and hydrogen. So that is called the equilibrium. Is at that moment we call the reaction has reached to an equilibrium. Okay, so forward reaction is equal to the reverse reaction at that moment, and as the result of concentration of reactant and product will remain unchanged. So at that moment, whatever the concentration, nitrogen, hydrogen, and ammonia achieved, not at the beginning, but at that when it first time it reached the equilibrium, at that moment, whatever was the concentration of the reactant and product, it will be the same all, doesn't matter how long you keep the reaction to go. 1 day, 2 days, 1 year, 5 years, The concentration will not change. And now you are smart enough to understand that we cannot allow this to happen in our industrial production, right? Because industry, they race against time because time is money for them, isn't it? If they can produce a product in 1 minute, and if another industry, they produce the same product in 5 minutes, they will not make as much money as that first one, that is they who are making the product in 1 minute. Although they're producing the same product, same price, but those who are making it faster, they will get more benefit. So we need to find out a way that we can achieve this equilibrium fast, because this is chemical phenomena that it will reach to that equilibrium, and you cannot bypass this equilibrium. You cannot say that, no, I don't want equilibrium, I just want ammonia only. No, you cannot have that. What you can do is you can do some engineering on it so that more ammonia produces at this equilibrium, or with less time, this equilibrium attained in less time or shortest time, so that we get faster the product. So that is why we cannot, we have to think in another way that how can we maximize the product in shortest time, right? This is another question we will see later on, how can we do that? But if we want to see the concentration of this, we do this diagram, right? We're going to see through the diagram the production and reactant of nitrogen and hydrogen and ammonia. What we'll see is this is the concentration, y-axis. This is y-axis, and it indicates the concentration, and x-axis, it indicates the time, right? So this is 0th time. Let's say this is 0 time. This is time 1. This is time 2. I do not know what is 1 hour, 1 minute, 1 second, but just consider this time. There is no unit here. So it's time 3. And this is concentration 1, 2, 3 as well. So from the reaction, we see that 1 mole of nitrogen reacts with 3 moles of hydrogen. That means 1 mole of nitrogen is here, hydrogen should be 3-fold. Or if there were 0.1 mole of nitrogen, I should have added at least 0.3 moles of hydrogen to get 0.2 mole of ammonia. I'm just saying that whatever is there, nitrogen, to get a stoichiometric ratio should be 3-fold. So that is why hydrogen is shown here 3. All right. At the 0th time. At 0th time means we have just added it. The reaction has not started. That is the 0th time. That hydrogen and nitrogen are just added. It's theoretical, of course, but just consider, imagine that you just put in that vessel hydrogen and nitrogen, the reaction has not started yet, although the reaction will start immediately with some condition, but just imagine that reaction has not started yet. It's 0th time, the reaction has not started. So at 0th time, the nitrogen will be 1, hydrogen will be 3, right? And then once the reaction starts immediately, and the reaction, at that moment, because reaction has not started, there will be no ammonia at that moment, isn't it? Because hydrogen and nitrogen have not mixed yet. How the ammonia will be produced? So at that moment, or 0th second or minute or whatever 0 time, that is no ammonia, and that is why ammonia started from this 0 point. And since hydrogen and nitrogen starts to mix immediately and to produce ammonia, so what happens is hydrogen also reduces from this side, nitrogen also reduces, but hydrogen reduces 3-fold nitrogen than nitrogen, because 3:1. So hydrogen, they started to reduce. Why they are reducing? Because they are reducing from the reactant side. They are going to the product side. They are going to the product side. And then that is the moment ammonia is increasing. Ammonia started to increase. From that second, that time, ammonia started to go up. The concentration of ammonia in the system, in that vessel, is start to grow up because nitrogen hydrogen mixing. And it is going down, but the interesting thing is, although it is not very, this graph is not very precise, but it gives us an idea that it was supposed to be like this, right? At some time, it would be 0 nitrogen, and hydrogen also would be, at this moment, it will be 0 as well. Because, and then ammonia will be produced like this, isn't it? But that doesn't happen. Hydrogen does not become 0. Nitrogen also does not become 0. And ammonia also does not become this 3 or 2. 2 actually. Because the reaction has stopped. The reaction has stopped there. Not too much. Only it reaches a little bit and the reaction is stopped. Reaction reaches to this moment where nitrogen is not decreasing, hydrogen is also not decreasing from the reactant side, and ammonia is not also increasing on the product side. What's the problem? So at this moment, we see the concentration of nitrogen, hydrogen, and ammonia is unchanged from 2 until how long you want to keep it. Doesn't matter. It does not change, all of them. So it is this is like this. So this is called that at second time or second minute, second hour or whatever time it is, they reached an equilibrium. Okay, they have reached equilibrium. Equilibrium has been established. All right, and from here, if we see it, put it on the graph, the rate of the reaction, all right, rate of the reaction decreases continuously. At the beginning, the rate was very high, but then the rate started to decrease. Rate means how fast the reaction goes to the completion or how fast the product is being produced. The rate of the reaction is decreasing and the product is going to increase, and at some moment they converge into a point or they coincide in a point where the rate is steady and the concentration of ammonia is also steady, because of course there is no rate anymore. But also the rate is not going to 0. The rate, there are some, I don't know what is the figure, there is not given figure, but let's, this is schematic diagram, so it is not actual figure, but it is showing that this is the trend. At this moment, the rate is not 0. It is some figure, 1 or 2 or whatever it is, because the reaction is going on underneath that whatever I can see, our visual barrier, the reaction is going on. So that is the equilibrium. The system is, so this yellow side, whole area is under equilibrium, or from here, the whole area, it is under equilibrium. All right. So we will talk about this equation later on. So this is part A. We will see part B as well. So when I tell you, you remember this slide, please. Analogy of dynamic equilibrium. Oh, so since the reaction is going on, I forgot to mention, since the reaction is going on, the rate does not become 0. The reaction is going on. So that is the reaction is keep going on. Product, some of them are going to product side, some of them going to reactant side. That means the reaction is going forward and the reverse. So this is a dynamic equilibrium. It's called the dynamic equilibrium, and most of the reaction in our real life is this type of both-way reaction, reversible reaction. Most of the reaction, in fact, all the organic reactions are this type of reversible reaction. Only few reactions that are explosive in nature, or it does not, produces some permanent changes. Those are the only one-way reaction. That is, one example is when we boil egg, right? The egg protein from liquid, it becomes solid. So this is changes, one-way change. But for your information, in 2011, I forgot 2015, one scientist, chemist, he found a way to reverse that process and won the Nobel Prize. So this is also not considered anymore the reversible reaction anyway. So, but that was just an example of it. Okay, so this is the dynamic reaction. That means forward and backward reaction does not cease, it keeps going on. So that is the dynamic reaction. Equilibrium law. All right, at equilibrium, now we are going to quantify. We want to see exact figure to understand. All right, so let's say that I hope that you can see, you already have the slide anyway. So equilibrium mixture A, B, C, D, we have 4 different equilibrium mixture. Like this reaction we are having, we know, but I am having 4 different concentration of this component and product, right? 1, 2, 3, 4, or A, B, C, D, right? For A, I have a nitrogen of 0.25 concentration mole. For hydrogen, I have 0.75 concentration, and then I am having ammonia of 0.074 molar concentration. For B, I am having more nitrogen, more hydrogen, more, of course, I'm getting more ammonia as well. So, and CD even lower concentration. So high and low both I am having concentration. Now I'm seeing that the ratio of this product and the reactant. All right, product, the concentration of the product, that is ammonia, the concentration, this third bracket, all right, from now on, as far as chemistry is concerned, when we consider this third bracket, it does not mean that it is in parentheses or it is in the bracket. It means whatever it is, oxygen, nitrogen, hydrogen, sulfur, phosphorus, carbon, whatever it is the concentration. All right, third bracket means the concentration. Third bracket means concentration in chemistry. All right, third bracket means concentration. The other brackets, first bracket or second bracket or this type of thing, that means exactly same what we mean for math or for other thing, physics. But third bracket means concentration. So now come back to this problem, table 1. That if we now take the ratio of the concentration of product, that is ammonia, and the product of the reactants concentration, we will get some ratio, right? We will get some ratio, and the ratio is for A is 0.39, for B is 0.25. So these are different ratio. It depends on how much product or reactant was used. The concentration of product and reactant were used. But if we take the ratios of their quotients as well, when we consider the number of moles, right? The number of moles of the reactant and product. Should I be writing here on a bigger scale? So this is nitrogen, and this is 3 moles of hydrogen. and it is producing 2 moles of ammonia. All right, so this 2 and 3, right? This is the number of moles. 2 moles of NH3, yeah, ammonia. So this is 2 moles of ammonia and 3 moles of hydrogen. It is being produced. Sorry, 3 moles of hydrogen is reacting. 2 moles of ammonia is being produced. So these 2 and 3 are actually the number of moles of that reactant and product, right? And that is why if we consider this quotient, we call it quotient, you consider this thing, and when we consider the number of moles, they will be used as the power of their concentration. So in third bracket of ammonia, we know this is the concentration of ammonia in third bracket. But when these two, this number of moles we are using, this is going to be powered. Do not use like multiply in front. It is totally wrong and you will get 0. Never use this. Always use the number of moles as the power for that species concentration. All right. So when we take the concentration, or I mean, what do you call it? The number of stoichiometric ratio. This is called stoichiometric ratio, or simply the number of moles. The power. It is called the reaction quotient. And this reaction quotient is always the same value. Does not matter what is the concentration you are using, right? What is the concentration you are using does not matter. You will, in the real life, these values, you cannot just take any value and put it here. These are from the experimental value. So if we take the value from the experiment, we will always see this is always, doesn't matter what is the concentration I started with this reaction. This reaction quotient is always same value, 0.052, 0.052. I mean, for 0.25, 0.75, 0.001, 0.001, whatever we start with, the nitrogen, hydrogen, we will always reach to this point where the quotient is always the same for all of them. And that is why it is called a constant. This is constant because it is not changing. It doesn't change with what is the concentration I started with. So this is called equilibrium constant. And it's represented by K. Okay, it is represented by K. Remember this one, equilibrium constant. Sometimes we see Kc as well, Kc, equilibrium constant. So this is at a fixed, it is, I mean, very important to remember that it changes with the temperature. It does not change with the concentration, what concentration is started with, but with temperature, it will change. Or pressure, does not matter what pressure you give. It will always have the same K, same, I mean, at all pressure, at all concentration, you will start it. But if the temperature is changing, this K is changing as well. So it is not 0.052 anymore. Let's say this is at room temperature, it's 25 degrees centigrade. So at 25 degrees centigrade, it is true, it is constant, 0.052. But if it is 35 degrees centigrade, we do not, I mean, it will be different. It is not 0.052 anymore. All right. So this is called a reaction quotient. And equilibrium constant. From this reaction quotient, we get it. So equilibrium, writing the equilibrium constant expression. How do we write the equilibrium constant expression? For any equation, just now we have seen it, for any equation, let's say that A and B, C and D all are the stoichiometric coefficient or the number of moles. For first of all, we have to balance the equation. If we ask you to write the equilibrium constant, the first and foremost thing that you will do is the balance of the equation. If we do not know the balance, if we don't establish the reaction first, the balanced equation first, we will not know the coefficient or stoichiometric coefficient or the number of moles for them, right? So it will be wrong. And once we know the number of moles or stoichiometric ratios, then we can start to add equilibrium constant. Kc will be the concentration of the species, right, in mole per liter or molar concentration. Oh, this is another important thing. Thanks for this. I forgot to mention, but it is here already. So it will be the concentration is always in mole per liter, not in gram per liter or whatever, but it is mole per liter. Mole per liter means molar concentration, right? We all know that it is molar concentration. So the concentration of all those species, reactant and product, will be taken in concentration, and the A, B, C, D, that stoichiometric ratios or those, what is the number of moles should be in a powered form. This will be power A and B. It is to the power. If it was 10, does not matter. You have to put it 10 here. So concentration of W power 10. That will be the thing that you should do if it was whatever value is there. Okay, sometimes student, it doesn't matter how many times I tell this thing in the class. Sometimes some student always do this. Okay, multiplied by 2. What is this? I tell so many times in the class and also in the tutorial. I keep talking about it. Some students still they don't listen. They put this, and then what will happen? The first thing, your formula is wrong. How can you get the correct answer? So sorry, 0. So don't do that mistake. Listen. All right. Okay, so another thing, homogeneous equilibrium, all species should be included, and for heterogeneous equilibrium, include gas and aqueous solution only. What does it mean? Right? Next slide, it will be more clear. So for writing example 1, it was supposed to be in the face-to-face class. Actually, I would give this thing, and this thing are not given to students, so they will have to write. They have to do the practice in the class, and I cannot enforce it now. This online class, but I hope that you just give a try for your sake, not for me, for your sake. Okay, so just give a try. Try to, even though it's given in here, here this thing, the equilibrium constant, but write it out, try it so that it will not look foreign when you are trying in the exam. Sometimes students, another thing I should tell you, I have another meeting here today. Forgot which. Oh no, I didn't accept that meeting. Okay. Another thing I forgot to mention. I should remind you actually. These all things are written on the, on this given on the slides. Looks so easy, but when you try, if you do not do it, practice at home in the exam, doesn't matter it's open book exam or whatever exam, it will look so difficult and so foreign. It will look like you've never seen it even if you do not try now. Believe me. Okay, so you must try at home. All right, so I mean, example, that is how do we write the homogeneous equilibrium? Homogeneous equilibrium, just remember the previous slide that we said all species should be included in the homogeneous. And for this case, all are in gaseous form. All in gaseous form. Heterogeneous will be, some of them will be gas, some of them will be other state, solid, liquid, aqueous, other thing. So that would be heterogeneous. So now for A, the Kc is nitrogen, a product over reactant. Okay, so this is, if I did not tell you, I'm telling you now. So equilibrium constant is product, concentration of product over reactant. Product over reactant, concentration of product over reactant. So product is here. For this case, you may argue that, oh, how do I know that this is the product or this is the reactant, because this reaction is going forward and this could be a product. That's true. That's clever actually. But the thing is, if we are asking you, if the reaction is written in this way, that on your left is the dinitrogen tetroxide, this is considered reactant, right? And on your right, this is considered product. And also, if we are asking you to find out the nitrate ion, nitrogen dioxide, concentration of nitrogen dioxide, so it is understood that you will keep it in the numerator instead of denominator, because if you do in denominator, then you have to multiply and then divide again, many steps. So yeah, okay. So the left side, easy thing is on your left is the reactant, on your right is the product. So nitrogen, concentration of nitrogen dioxide, and then this one is going as a power 2, and here there is nothing, 0, so it is 0, and we don't need to write 0, so no need to mention here. For B, same thing, nitrogen dioxide, but here it is half. Both are the same reaction actually. It is half produces 1, 1 produces 2. So half, and then this half is going here. And here it is nothing. Sorry, it's not 0, it's 1. Oh my God. Sorry, what I did. It is 1 actually. So 1, we don't need to mention it here, but we can mention. If you want, you can. And this is the same thing goes. For this case, it will be third bracket as well. And I forgot to put it here, but now I am putting it. All right, so this is for the homogeneous equilibrium. For a heterogeneous equilibrium, this is solid, this is solid, this is gas, right? So any idea what should I write for the Kc for equilibrium here? What will be the Kc for this case? It is only the carbon dioxide. All right, it is only the carbon dioxide, and there is nothing, there is only 1 here, so it is only 1 here and nothing else. We don't need to include this thing because they are solid, and solid does not have a vapor pressure, and that is why there are other reason, but remember that solid and liquid no need to be included, but gas and aqueous, yes, they should. All right, so this is how we would write for the equilibrium constant for this. And here it is. For ethanoic acid or vinegar, this is the vinegar or ethanoic acid, acetic acid also is called. Vinegar means it is acetic acid, but when the 5% of it in the water, then only we call it vinegar. Not this thing necessarily is vinegar, this is acetic acid, but when this is 5% in water, we will call it vinegar. Okay, so vinegar, acetic acid and water is producing water, what do you call it, hydronium ion, because it is an acid, I don't need to put it on my head. Don't talk. So hydronium ion it is producing, and then it is producing acetate ion, right? So in this case, how many of them should be included? This is aqueous, this is aqueous, this is aqueous as well. But this is liquid. I will exclude this one because I don't need liquid. Liquid also does not have that. In liquid state, it does not have the vapor pressure. So it has, but it's minimal. Anyway, so this is the thing that I will put it, and KC is this negative and positive, it changes from here, and it is should be here actually, but why it is gone there, and there is nothing else in front, so I don't need to add anything else. What does an equilibrium constant tell us? So far we have been talking about the equilibrium constant. What does it tell actually? What is this thing that it tells us? So typical equilibrium, like if the K is bigger than 0.0001, but it is less than 10,000. So what will happen? There will be significant amount of reactant will be produced. So if K, for this case, let's say this K is, how do you say that? Let's say it is 5, right? It is 5. So this 5 is between these two figures. It is more than 0.0001, and 10,000, right? So anything, any 100, 1,000, 1, 2, 5, 10, whatever the value is, the more the higher, of course, right? So whatever the value, then we will consider the K value. If it is in between this, we will consider the reactant will produce significant amount of product will be produced in the system. So there will be less amount of reactant, but most will be the product. Of course, the higher the K, the more the product will be produced. And if the reaction, K value is more than 10,000, then what? There is very small amount of the reactant or no, but mostly the product has been produced. Or this, in this case, the reactant is, a reaction towards forward reaction only, not backward, reverse reaction, only the forward reaction mostly. But when it is less than 0.001, that means the reaction has not even started, or sometimes even started, this very small amount of product has been produced. So in these two are the good cases for a reaction to be in equilibrium. All right. These are the two cases that will be in equilibrium thing. Okay, so now effect of temperature on K. What is the effect of temperature on K? Last lecture you have already seen, or last tutorial you have already seen that we talk about the exothermic and endothermic reaction. Exothermic means the heat is produced as a product from the reaction, right? The heat also produces along with the product from a reaction, right? So this is an exothermic reaction, and endothermic reaction is heat is required. I need to provide heat, just like I need to provide the reactant, so that the reaction will go first. But for exothermic reaction, the K or equilibrium constant will be reduced. All right. But for endothermic reaction, the K increases. So the more, for exothermic reaction, the more heat, the less product will be produced if the heat is more there. But for endothermic reaction, the more heat I provide, the more reaction will provide. More product will be produced. So the K will be more higher. And that is the relation with temperature to the K or to K, yeah. Okay, now there are some examples. So it says that calculate the values of the equilibrium constant for the reaction represented by the equilibrium equation. Sorry, so hydrogen and oxygen and hydrogen and iodine. It is producing hydrogen iodide, and this is a homogeneous reaction because all of them are gas, right? All of them are gaseous form. And almost 1 hour. And then at 460 degrees centigrade, if a 2-liter vessel contains an equilibrium mixture, read the question, yeah. If at 460 degrees centigrade, the temperature apparently not needed if it is not an endothermic. So if a 2-liter vessel contains an equilibrium mixture of 0.0860 mole of hydrogen, 0.124 mole of iodine, and 0.716 mole of hydrogen iodide. That means the reaction already in the equilibrium and it is containing all of them, hydrogen iodine and hydrogen iodide. So what is the, how do I write the equilibrium constant and what will be the equilibrium constant for that reaction? The trick is, remember that they only say it is mole, mole and mole. But as I said, that it only consider mole per liter. This third bracket means concentration and only it means moles per liter, right? So at 2 liter, so how do I feel? I mean, find the concentration. I have to divide by 2. So that is simple and easy. Not always, but for this case it is easy. So by 2 I will divide and I will find mole per liter for this. And Kc, of course, is homogeneous, so all of them will be included here. All of them are gas. It is. And number, I mean, concentration of hydrogen and iodine and hydrogen iodide, all of them divided by 2, so mole per liter we find, and then from this we find the volume, and this is 2 here, so 2 is power. Another example is this, so this one, and the equilibrium constant for the reaction described by the equation, this is 4.5 molar at 80 degrees centigrade in an equilibrium mixture of this temperature. What is the concentration of nitrogen dioxide if the concentration of nitrogen tetroxide is 0.0012 molar? So from here it says that at equilibrium how much nitrogen dioxide I will get if I start this reaction with this molar of nitrogen dioxide, dinitrogen tetroxide, and the equilibrium constant is given as well, right? So from here we see that this is needed and this is given, or we find it from the reaction, so it's easy to find it. Another example for this problem is the equilibrium constant for the below reaction is 4.5, right? The Kc is 4.5. A gas mixture in a 2-liter vessel at 80 degrees centigrade contained 0.2 molar of dinitrogen tetroxide and 0.3 molar of nitrogen dioxide. Decide if the reaction is at equilibrium, and if it is not, predict the direction of the reaction will shift to the equilibrium. First of all, we have to find out whether it already reached the equilibrium or not. And if it reached the equilibrium, if it is not, if hasn't reached the equilibrium, which way the reaction will move, whether it will move to produce more nitrogen dioxide, or it will move this way. That means already there are too much nitrogen dioxide, so the reaction will go backward. So we have to find out. In the same way, there is the reaction quotient. All right, the reaction quotient, that initial concentration. All right, If initial concentration is equal to that reaction equilibrium concentration, then the system is an equilibrium. There will be no changes in reactant or product. But if initial equilibrium quotient, okay, this reaction quotient, sorry, not equilibrium, QC is reaction quotient and Kc is equilibrium constant. So if this reaction quotient is less than equilibrium constant, then the reaction will move right. That means more product will be produced. And if it is more, then the reactant will move backward or reverse and more reactant will be produced. So from this reaction or from this problem, it says that a gas mixture, the concentration in 2-liter vessel as well, and there are a number of moles is given. So only the thing is, when we find the initial the quotient, all right, the reaction quotient, when we find, we consider the concentration or at the initial stage of the reaction, at the beginning of the reaction. So this is at the beginning, 0.3 molar of nitrogen dioxide and 0.2 molar of dinitrogen tetroxide at the initially, and we find it is 0.23 constant. I mean QC, it doesn't have any unit, is 0.23, and Kc is 0.45. So Kc is much bigger than QC, and it is not equal. So if it is Kc is much bigger, right? Kc is much bigger, so the more product will be produced. Or QC is smaller than less than Kc, so more product will be produced in this system. This is another problem here, and it says that a mixture 500 mole of hydrogen, 500 mole of iodine was placed in 1 liter stainless steel flask at 430 degrees centigrade. The equilibrium constant Kc for the reaction is this Kc is 54.3 at this temperature, at this 430 degrees centigrade. It is Kc is 54.3, right? So calculate the concentration of hydrogen, iodine, and hydrogen iodide at the equilibrium. So what will be the concentration of hydrogen, iodine, and hydrogen iodide at the equilibrium? First of all, this is one thing that I need to produce a ICE table, because number of moles is given. The Kc is also given, so I know Kc, and I can also formulate the Kc is hydrogen iodide, and this is squared because there are 2, and then hydrogen and iodine. Oh, another thing I should mention here, that there are 2 different things, right? These 2 and these 2 are different. This 2 is, first of all, let me erase it here. So this 2 is the number of molecules are there. Sorry, number of moles are there. Molecules sometimes. So number of moles are there, but these 2 are the atoms, number of atoms. If I use it 3, it is not iodine changes, this identity changes. But if I 3 here, it does not change. It's the same thing, only more hydrogen iodide is there. I refer to more hydrogen iodide is there. But if I 3 here, there is nothing like this. The whole space is the identity changes, right? So these 2 and that 2 are different. And that is why we should be careful. And this 2 means this 2. But this 2, the atom, number of atoms, is here. It does not go power. All right, so don't make this mistake. So now this Kc, now for this problem, the Kc is given 54.3. And I have this 500 moles, 500 mole, everything is given. So what is the problem? Why, I mean, what is the required? The thing is, I have this 500 moles at the initially, right? I have, this is at the initial, but at the equilibrium, how much was there left? Because I know that not everything will be finished, because this is a reversible reaction. So not just like nitrogen and hydrogen and ammonia produces, I said that doesn't matter how long you keep it, nitrogen and hydrogen is not going to finish, right? It will stop there at some point. So it is not finished. Hydrogen and iodine also will not finish. There will be leftover in the system. How much is left over in the system at this moment? This is being asked, that at equilibrium, how much of this hydrogen and iodine is left in the system. So to find out this thing, we need to find out, we have to do a specific strategy for this, is called the ICE table. Okay. Okay, ICE table, and then this is initial change and equilibrium. This is called ICE table, ICE table, initial change and equilibrium. So at initially we had 0.5 molar of hydrogen, 0.5 molar of iodine, but at the initial moment there was no reaction, so there was no hydrogen iodide in the system. But at the change, right, how much of hydrogen and iodine reacted? We do not know how much they reacted. So we just consider that X amount of them reacted. And since it is 1:1 reaction, right? So if there is 1 mole of hydrogen iodine react, of course there will be 1 mole of iodine has to react there, because it's 1:1 reaction. So if there is X mole of hydrogen reacted, X mole of iodine will be reacted as well, right? So this is a negative sign because initially I had 0.5 molar and I am having this X mole deducted from there, breaking from there. From this 0.5, this X mole is being deducted, being broken down from this 0.5. Same goes for this iodine as well. So this X and X, it is going there and it will be twice X because this is 2 is here. So whatever is produced here, there will be multiplied by 2 because the reaction stoichiometry ratio is telling us that. That is 2. So if that X amount has been deducted or reduced from this 0.5, how much at the equilibrium is there? The hydrogen and iodine is left over. 0.5 minus X is easy, right? 0.5 minus X. And there is nothing. 2 ice X plus 0.000 is still 0.2 ice X, doesn't matter. So like this. So now we have this, the concentration at equilibrium, and this is in concentration. Yeah, this is in concentration. We consider this concentration. If it was not in concentration, given 0.5, we had to convert it to concentration. 0.5. All right. So now we will write the equilibrium constant for this reaction, and this is the equilibrium constant, and we'll just plug this value in to this equation. And by plugging the value, we find that X, right? We find the value of X, and the X, we equate this both sides, take the root square, and whatever we find, we solve this problem out. How do we solve the problem out? We'll see it in the tutorial, or you can try at home as well. So this is the X value is 0.393 mole. So, and this is not the answer that is asked. The question asked, what is concentration at equilibrium? So we have to deduct this thing from this 0.5 to get the equilibrium constant. Okay, so since equilibrium and from here, and we will get, this is the value that we are getting. So 0.5 minus x, 0.5 minus 393 is 0.1, 0.1, and times 2 is 0.786 is hydrogen iodide is produced. Okay, and there's something, how do you validate your answer is correct or not? Okay, so another example of similar type, that at a particular temperature, 0.5 molar sulfur dioxide, 0.1 molar of hydrogen, oxygen, and 0.15 mole of sulfur trioxide were mixed in a 2-liter vessel and allowed to reach equilibrium according to equation, this thing, right? Analysis showed that 0.14 mole of sulfur trioxide was present in a gas mixture at equilibrium. Calculate the value of equilibrium constant at this mixture. So the same thing, I have to do the ICE table and find out the concentration first, number of moles were given, and then number of moles were given, and the vessel was 2 liters, so I had to convert it to moles per liter, so divided by the volume, and we find this is the concentration. And afterwards, we found that this is core. I mean, this problem, it says that 0.5 mole of sulfur trioxide, 0.01 mole of high oxygen, and 0.15 moles of sulfur trioxide was present. So 1.5 mole of sulfur trioxide was present, and it is in 2 liter, right? So 0.07 mole per liter concentration of sulfur trioxide. Now, how do I know that I have 0.005 have to be, deducted or added here, right? This is both way reaction, and 0.075 is produced. So what will happen is this one is breaking down because of sulfur oxygen. Oxygen is 0.005, right? So oxygen is 0.005, and then it is 1:2. For oxygen, it is 1:2 reaction. 1 mole of oxygen, 2 moles of sulfur trioxide is produced. So whatever oxygen is there will be deduced from here or produced here. The same amount of sulfur trioxide, double of sulfur trioxide actually, because 1:2, has to be broken down from here. All right. So since 0.0025 moles of oxygen is being changed or added up, so sulfur trioxide is that amount, double of that amount has to be broken or dissociated from this. And since sulfur trioxide is dissociated, oxygen and sulfur dioxide, because only oxygen cannot produce, sulfur dioxide will also be produced. So this is produced, and 0.005 is added up with this 0.25 in this case, and the final or equilibrium concentration is not final concentration, it's equilibrium concentration anyway. So this is both added up together. So we plug this value in here. Sorry, this is not the value. So this is the value we add in this case, and here it goes to here. From here we find that the Kc is at this temperature 726 for this case. All right, so for just take maybe, we don't have much time, but maybe 2-3 minutes. I just go and make some tea for myself. It's very hard to talk to myself. All right. So break for 5 minutes. Right. Hello guys, you are here there. I hope you are there. I'm here too. And hope you're refreshed. So I hope you are still there. You didn't leave. Some of us left. Okay. Anyway, so now here we are. Factor affecting equilibrium position. Actually, I have one Menti question. I should have. I just remember it, and then okay, we will go for that later on at the end of this presentation. So factors that are affecting the equilibrium position. We have already said that only temperature that has some effect on the equilibrium, and when the equilibrium changes are imposed to a system at an equilibrium, the equilibrium will be disturbed, like addition or removal of substance. It does not matter how much of the reactant or product or the substance or species you are adding it, the equilibrium will attain, but with some time, maybe. All right. So equilibrium is like, let's say that for hydrogen iodine, you put them there and equilibrium attained, and then you are adding more hydrogen suddenly. So what will happen? So the reaction will move forward to hydrogen and producing more hydrogen iodide. So the equilibrium will go forward, right? Equilibrium will be more. That means the Kc value will be more because more hydrogen iodide will be produced in the system. Of course, if we change the temperature without adding anything, without adding any single species into that, if we change the temperature, the equilibrium constant will be changed. Change in pressure of gas concentration of the solution. Concentration of the solution. Yes, if we change the pressure, because the pressure has some certain effect, we will see it now. It will also shift the equilibrium constant will not change, but it will shift towards a side where it can withhold this type of changes. And exactly this is the same thing that is Larshor is telling us. The Larshor's principle is telling us that it is used to predict the consequences of these changes on an equilibrium position. The equilibrium position will shift towards to right or backward to left, that means to reverse side, in order to re-establish the equilibrium, right? Like if we rotate a coin, sometimes we see that the coin rotates very fast on the, and if you touch it, after some time, I mean, it's just an analogy. After some time, the coin will fall flat on the table, but during this rotation, if you touch slightly that coin, what will happen? It will move from there and then go change the position and start to rotate again. So that is keep rotating actually. So that is, it is changing the position, but still it is in equilibrium. All right. So that's what Larshor is saying, that if we disturb a system where it already have attained an equilibrium, if we disturb that system by adding or removing substances or species, or increasing temperature or decreasing or increasing pressure, that it will move towards or backward in a way where it can withhold or it can nullify those type of changes on it. Okay, so addition of what happens if Larshor's principle predicts that addition of a substance, reactant or product happens. If the addition happens, then the system will oppose the change by shifting the opposition side in order to reduce the amount of substance. Like if I add more reactant, it will go to opposite side, means product side. If I add more product, it will go to the opposite side, means reactant side. Or if I remove more reactant, so it will go to this reactant side to fill up that gap. If I remove the product from the system, it will go towards the product side to fill up that gap, right? So if you add more, it is not taking, it is going towards the other side. If you remove something, it is not also accepting, it is filling up that gap, right? And the Leur-Shortlist principle can be visible in a way of adding a substance through this graph. And we are going to finish soon, hopefully, so that we have some time for that Menti question. So adding a substance. This is what I was saying, that is the part B, all right? This is part B. The part A, we have already seen that here is the part A. This is the part A. Part A of that presentation, right? That hydrogen and nitrogen were added and ammonia were produced in the system. Hydrogen and nitrogen I added to the system and they gradually reduced. It is not drastically, it is gradual, slowly. I call it slowly. I mean, I don't know at the time, but it looks like it is gradually is going down, hydrogen and nitrogen, and ammonia is gradually increasing in the system. But this is where the part B is. Part B is this one. And this is what we are seeing in that current, I mean, we are going there to, I was referring to. So this position is part B, where the system was in equilibrium already. It is attaining the equilibrium. So this part A should not write here, actually should write here. This is part A, P1. All right. So let's go to part B now. So part B, we see that the system was in equilibrium, but suddenly it was nice equilibrium, no changes, anything. Until here, maybe let's say for 5 minutes, until here it is 5 minutes, right? It's 5 minutes. Let's say, I don't know, maybe 5 minutes, 10 minutes, 1 minute, whatever minute. It was no changes, but suddenly after this equilibrium, it was in equilibrium. And then I see that this is a drastically changes, suddenly changing. The ammonia concentration is suddenly increases. So what's happening here? What is the problem? And the ammonia is increasing, and as along with ammonia, hydrogen and nitrogen are also increasing, but they are gradually increasing like this. Gradually increasing. Of course, hydrogen will increase more because there are 3:1. And nitrogen, it is not, hydrogen is not increasing like this, nitrogen is not increasing like this, but they're gradually increasing. But the ammonia, it increases like this, right? It's like a peak. So what is happening here? The thing is, because this ammonia is increasing at 1 instant minute. This is 1 minute, right? 1 second. At a single second, it is increasing. At that second, it is increasing. And then, of course, it is gradually decreasing. But at that moment, it is increasing at a single time. And it happens because I have added some ammonia into the system. Artificially, I have added. And when I added the ammonia, of course, I added at, I just opened the valve at time t, or 5th second, 5th minute. I added like a few concentration, few moles per liter of ammonia, and then I close it. So that is why the peak goes up and then started to decrease. So when it is started to decrease, this hydrogen and nitrogen started to gradually increase, because the system, according to Leur-Shortlist, if I add this one, the reaction, the equilibrium will shift to left. If I add product, the equilibrium will move towards the reactant side, and that is why that means ammonia constant is increased in this case. So equilibrium shifts to backward to the left side. And again, another thing, the opposite thing is I am reducing ammonia at that single moment. At that single moment, I'm reducing, I'm removing, I'm taking out. I open the valve, take the ammonia out of that system, and then close the valve again. So that is why the concentration suddenly, drastically, it is reduced, like that. And then again, it start to increase. Since ammonia started to increase, of course, hydrogen and nitrogen will gradually start to decrease as well, because the equilibrium shift forward. That means equilibrium shift towards the ammonia side, the product side, because product has been removed. So this is what the Le-Chatelier's principle is telling us. Okay, predict if the equilibrium system is in equilibrium, then if it is heated, it will oppose the change by favoring the endothermic reaction. As it will happen, the system to cool down again. And if it is cooled, it will oppose the change by favoring the exothermic reaction, as it will help the increase the temperature again. So it will always keep a balance on it. Whether it is for materials or whether it's for heat or whatever, it will always keep a balance. Okay, if you take out too much heat, it will produce heat. If you give too much heat, it will cool down to remove that heat. Okay, and it can be visual from this side that ammonia started to decrease, right? Gradually, it is not a drastically, it is not like this. If it is like this, reducing or this increasing, then we understand that you have removed it or you have added it. But it is gradually decreasing, and then hydrogen and oxygen gradually. So it was in equilibrium at this position. At this position, you see what happens that it increase and decrease suddenly. What went wrong, or what was the problem here? The problem is we know that this is an exothermic reaction. This is an exothermic reaction, and ammonia started to reduce. Exothermic reaction, that means it produces heat. It produces heat, and I am adding more heat to that system. I am giving some more heat. I'm heating it up. The whole vessel, I am putting some heat into that vessel. So what will happen is the reaction will go backward to remove, to how to say that, to counter that added heat. To counter that added heat, the reaction go backward or reverse, and that is to. There is no way that it can keep ammonia and go backward. If it goes backward, the more ammonia has to be dissociated. And then ammonia is being dissociated. That is why nitrogen and hydrogen is produced. So hydrogen and nitrogen is being produced. Of course, hydrogen produces more because 3 and ammonia. So this is because there is no other clue why suddenly ammonia is getting reduced, hydrogen and nitrogen increases. So because of this, heat increases in the system. And after some time, it reaches the equilibrium again. There is no changes, you see, it's in equilibrium. It's very calm and quiet and very comfortable. It's equilibrium. All right. So this is why the changes in temperature happens. Another thing is, suddenly if we remove the ammonia, all right, suddenly it looks that ammonia has been removed from the system, and it is drastically removed from the system, right? So what is happening is the concentration of ammonia has been reduced from the system, that we have already seen removal of the system. All right. And then if that is okay, now this slide came in between. So this was heat was increased to the system, and if heat is removed from the system, if heat is removed from the system, what will happen that the reaction is producing heat, and I am somehow removing the heat from the system. Is there any idea? Somebody can tell me. I cannot see yours. Oh no, I can see. So how can you remove heat from that vessel or from that system? Any idea? Anybody wants to say or wants to participate or help me out there? How can I remove the heat from this? I know how to add heat because I can just put some fire there and it will be heated. But how can I remove the heat from that system? Anybody? Hello, can you hear me? Ice cube, thank you, Elva. Good, smart thinking, yes. We have to put ice cube so that the heat is being dissipated or has been absorbed. Or what you can do is you can blow air, cool air to that so that it takes the heat away from that. So Elva is the savior for us today, for you guys today, okay? Remember this. She helped it out. All right. Okay, so now if we decrease the temperature means we remove the heat. What is happening is, you know, this ammonia is increasing because the system will move towards the side that it will produce more heat because you are reducing the heat, and then ammonia is being produced. And this is the principle that is being taken into the sorry, this is a good principle, but I mean to produce mass production of ammonia. But problem is removing heat. Or in the industrial level, it is hundred of tons of the ammonia. It's not 1 mole or 2 moles, right? They make it tons of it. How much ice cube would be required? It's too much. They cannot afford it. So what they do is they remove this ammonia from the system. They remove the ammonia from the system, not removing the heat. If they remove the ammonia, the more ammonia will be produced. So this is how they produce more in a short time. Okay. What about the pressure? We have seen that if we increase the pressure, that means in the piston, we pressurize it. So the system, the pressure increases in the system, right? Another thing is we increase the concentration or volume of inert gas into the system. If we add the inert gas into the system, in the container or into the system actually, so the gas pressure is also increases. If the gas pressure increases, what will happen is the system will move towards a side where there is less number of moles. Where is the less number of moles now? Right here. If we see where less number of moles or less number of particles also can call. So this is 1, this is 3. So 3 plus 1, 4 particles on this side. This is 2 particles. So if I increase the pressure, the gas, I mean in the system, the gas will move towards this side. And in this case, we are not considering the temperature or concentration or whatever. If we increase the pressure, it will go towards the less number of moles. Or if you decrease the pressure, then it will have a much free and good time, comfortable stay, so that they will move towards this more particle side. So by increasing pressure, we can also, for some reaction where the product side is less particle or less number of moles, so that we can produce more particle, more product in that way. Decrease the pressure in gaseous system. In this case, we see that here, suddenly the hydrogen and nitrogen is removed from the system, right? And also, I mean, let me take another color here, maybe this color, much brighter. So this is, you see that it is removing at this side. So what is happening is suddenly at this point, all the pressure was decreased. All the whole system, the pressure, whole system was decreased. So I mean, volume was increased. The pressure was decreased means another thing. It looks a bit controversial, but it's not controversial at all. Oh, gone all. Okay. Okay, so this is, let's say, our reaction vessel, right? This is a reaction vessel, and this is tight. It's closed system. How can I increase the pressure? I mean, decrease the pressure here. Somehow I increase the volume to be bigger, right? I increase the volume of the vessel to double. Then the pressure will be reduced. How can I do it? I mean, add these two together, and then I open the valve here, so all of them go out to the bigger space, and then the volume will be increased. The pressure decreases in this. So when the pressure is decreases, it will go backward. The more hydrogen and nitrogen is produced and more ammonia, you see, the more ammonia is being dissociated, or I mean gone actually from the system. All right, so because more, this is the more high number of moles side, it goes to the number of moles side. All right, so this is dilution. For those who are in aqueous medium, if we add water to the aqueous medium, dilution, if we do the dilution and the concentration reduces, so it will go to the more number of mole side. For this case, it is 1 mole of ferrous thiocyanate ion. Okay, it will go, if I add more water to this system, it will become more iron and thiocyanate. More iron and thiocyanate will be produced, because if I add more water, that means the volume increases. Right, the volume from 1 liter I add 5 liters, so 5 liter volume increases. From one small bottle, 1 liter of a small bottle, I make it 5 liter gas. From a small balloon I make it big balloon, so the gas pressure reduces, right? The big balloon. So the same content with the same content. Anyway, so that is how, if we add water or solvent, is similarly we can remove the pressure, or the pressure can be removed and the system can move towards where the number of moles is. This is German chemist, the Haber, and this German chemist is he was a hero, then he has some controversy. He, from hero to he became a villain, actually, to some extent, people say, because he produces this ammonia, this system, Haber process, and because of him, actually, we become more self-sustained, sufficient in food production. Because of the ammonia, we produces more urea, the fertilizer. And this process, Haber process, he made up. Before this, we knew how to know ammonia, but we didn't know how to make it in commercial level to make it more efficiently. He found out that if we remove the ammonia and remove the heat as well, the more ammonia will be produced. And because of this, he passed the Nobel Prize, and then his controversial participation in World War I. Also, World War II or World War I, I forgot, also made him notorious for this gas. Okay, so this is the condition of our Haber process. This is a catalyst. In presence of catalyst, it produces more ammonia and faster. in this pressure and in this temperature. Okay. All right. So this is the example that we have seen today and summary for this. And I'm going to this Menti question. Please go to this menti.com. Before that, anyone has any questions so far? Anybody has any question? All good? Alex, all good? No one has any other question or don't know even if you have a question? Oh, okay. All right, so please go to the menti.com and then use this. Okay, let me use this code 9580 95801595. Yeah, and do your voting. Let me share this with you. Okay. So sodium bicarbonate produces sodium carbonate, carbon dioxide, and water. Okay. In a 2-liter reaction vessel, there are 3 moles of sodium bicarbonate, and after the reaction reached at equilibrium, there were 1.5 moles of sodium carbonate, 0.5 moles of carbon dioxide, and 0.7 moles of water. What is the Kc, that means equilibrium constant, for this reaction? I know that you can see the screen, so please do it. We have only 2 minutes to go. Somebody has a question? Why? Oh, okay, voting is closed. Sorry. Yeah, now voting is open. Thank you. Timothy, Elva, thank you, thank you. Now you can vote. Vote it faster. One vote so far. Two votes. Faster. Okay, I start counting time. Out of this 15 students, only 4 votes so far. Okay. 1 minute. 30 seconds. Twenty seconds. 10. 1. Only 8 students vote so far. Okay. Now the thing is, first of all, what do we need to do? We need to do the concentration first, right? It says that it's 2-liter vessel and there are 3 moles of sodium bicarbonate and 1.5 moles of sodium carbonate, and carbon dioxide is 0.7 mole. No, sorry, 0.5 moles of carbon dioxide, 0.7 moles of water. We don't need to calculate all the concentration because Kc, we have to only consider, this is a heterogeneous system, right? And we have to consider only those are gas or aqueous. We see that sodium bicarbonate is solid, sodium carbonate is solid, carbon dioxide is aqueous, and water is aqueous. So only carbon dioxide, of course, carbon dioxide should be gas actually, but I just made it aqueous. So to make you more confused, so that you become more, strong, robust, so that later on in the actual test you will not be confused. Carbon dioxide should be gas actually, but just to make, to see whether you see it, are you paying enough attention or not? So that carbon dioxide should be gas. Anyway, so we only consider carbon dioxide and water, right? So the Kc depends on the concentration of carbon dioxide and water here. So we only consider the concentration of carbon dioxide and water, and concentration of carbon dioxide and water is 0.5 over 2 mole per liter. So 0.5 moles in 2 liters, so 0.5 over 2 mole per liter, and 0.7 over 2, and that will be the concentration, Kc. So Kc is equal to concentration of carbon dioxide, third bracket, and concentration of water in third bracket. That's it, because the rest two are in solid, so we don't consider them. And this carbon dioxide and water should be in mole per liter form, so that you will get the Kc, right? So this is it. And right, so any other question anyone else has? Any question? All right, Alex, thank you. So okay, thanks for this class today. I'll stop recording. And